Hi, I am the COD AI supporter. Let us go straight into bubble sort. The algorithm compares adjacent pairs, swaps them when the order is wrong, and after each pass the larger values drift toward the end. The interesting part is that bubble sort is easy to explain, but not always worth using. If the data is almost sorted, it can move lightly. If the data is reversed, almost every pair must be checked and swapped. In other words, the same algorithm can feel fast or slow depending on the input quality. Before we run the chart, hold on to the main question. Bubble sort fixes local pair mistakes, and the cost grows when there are too many of those mistakes. The core idea is very human. Do not solve the whole list at once, just fix neighboring pairs. If the left value is greater than the right value, that local order is wrong and needs a swap. If the pair is already correct, skip it and inspect the next pair. Repeating this from left to right gradually pushes the largest unsorted value to the end. With the array 5, 1, 4, 2, 8, I will narrate the actual flow. First compare 5 and 1. 5 is greater than 1, so we swap and let 1 move left. Next 5 meets 4. Still out of order, so swap again. Then 5 meets 2. Swap again, because 2 belongs before 5. When 5 meets 8, there is no swap because 5 is smaller than 8. After the first pass, 8 is locked at the end. The next pass keeps fixing the remaining mistakes, such as 4 and 2, until a full pass has no swaps. Now I will narrate close to the animation. When the pointer sits on 2 cyan bars, that is a comparison. If the left bar is taller, the order is wrong and the algorithm moves into a swap state, usually shown in orange or pink. For example, 5 before 1 must be swapped, because ascending order does not allow a larger value before a smaller one. After the swap, 1 moves left while 5 keeps being compared with the next value. If it meets 8, there is no swap because the order is already correct. Each pass pushes the largest remaining value to the right. The green region at the end is no longer something to guess about, it is locked. This is the detail that makes bubble sort less naive. Here's how the swap flag works. At the start of each pass, assume no swap has happened. If a swap occurs during the scan, the flag turns on, meaning the list still has local mistakes. But if a full pass finishes with no swaps, every adjacent pair is already in order. At that point, the algorithm has proof to stop immediately. In memory, bubble sort is compact because it sorts in place and barely needs extra storage. The cost is time. With n values, one pass must inspect many adjacent pairs. On reverse data, almost every inspection leads to a swap, so the work grows quadratically. That means the video may add only a few more bars, but the number of comparisons and swaps rises sharply. So is bubble sort useless? No, it is excellent for learning how algorithms think through comparisons, swaps, and invariants. With tiny data, or nearly sorted data plus early stop, it still has a place in demos and lessons. But once you move to large data or production systems, leave bubble sort in the classroom. When performance matters, use the built-in sort or stronger algorithms such as quick sort, merge sort, heap sort, or tim sort. To recap, bubble sort is not the choice for large data, but for understanding compare, swap passes, and early stop. It is a wonderfully visual stage. Once you see this rhythm, more advanced sorting algorithms become easier to approach.